Okay, today we're going to do calculus on vector valued functions, okay, which means we're going to do limits, derivatives, and integrals of vector valued functions. Now, we can say this. I could write the limit of r of t. Let me make this a little bit smaller, actually. Okay, so I can write the limit of r of t as t approaches c equals L. Well, that would be a vector, right? The limit of a bunch of vectors would have to be a vector, okay? So I can write that if for every epsilon greater than 0, there exists a delta greater than 0, such that if the distance between t and c is greater than 0 and less than delta, then the distance between r of t and L is less than epsilon. Now, how do you measure a distance? Oh, that's a vector, by the way. How do you measure a distance between vectors? It is the magnitude of their difference. Okay, so that would be the definition of the limit of the vector valued function r of t as t approaches c. It looks very similar to the limit of a real valued function that we learned in Calc 1, right? But here's the deal. Because it's so similar, and because you learned all that stuff in Calc 1, you can use that. You don't have to start over again from the beginning here, okay? And a much easier way of writing the limit of a vector valued function is to use what you already know about limits of real valued functions. And I would rather write this. If the vector valued function r of t equals, okay, the vector, where you would have an x component and a y component, so let's call those f of t, g of t. Okay, so if that's r of t, then the limit of r of t as t approaches c would just equal the vector that has the limit of f of t, comma, limit of g of t. You see, if r is a vector valued function, then r is just made up of a vector with two real valued functions in it. And so the limit of this vector valued function is just the vector that has the limits of the real valued functions. That's a much easier way to do it rather than doing the whole epsilon delta thing all over again. Okay, same thing for derivatives. We could write just a second here. Sorry for the pause. Okay, for derivatives, we could write r prime of t equals the limit as h goes to 0 of r of t of h, t plus h minus r of t over h. That looks very similar, doesn't it, to how we define the derivative of a real valued function in Calc 1. Well, again, because it's so similar, then why don't we use what we already know and write it that way? It's much easier to write if r of t equals the vector f of t comma g of t, then r prime of t is going to just equal the vector f prime comma g prime. Okay? So let's practice a couple of problems. Well, here's one good problem here. Let's have r of t equal the vector t squared comma t. Okay? So let's find r prime of t. It's very easy, isn't it? It's just going to be 2t comma 1. That's the answer. See how easy that is? Let's continue with that. Let's graph r of t, and also let's graph r prime of 1. Okay, I'll show you this picture. Okay, so that blue parabola is our function r of t. Okay, now what's r prime of 1? I didn't write it down, did I? So let's write it down. R prime of 1 would equal the vector 2, 1, correct? So you can draw that here. There's r prime of 1. It's the vector with components 2 and 1. But it makes more sense if we draw it here. I don't like the way that changes the color, so let me use yellow instead. Makes more sense to draw it there, and here's the reason why. This point right there that's the point 1, 1. In other words, it's the terminal point of the vector r of 1. You see, r of 1 is the vector 1, 1. And that would put you at this point right there. So it makes more sense if we draw the vector r prime of 1 originating from that point. Okay? Then what you have is you have what's called a tangent vector. What I've highlighted in yellow there is a tangent vector emanating from the point r of 1, okay, and it's the vector r prime of 1 originating from that point. It is tangent to the graph of r of t at the point where t equals 1. In fact, let me even write that. Let's write t equals 1. Okay? So, very easy. Now, integrals are just as easy. Let's add some space in here. We could do the whole Riemann sum business here, but we don't have to. All we have to write is if r of t equals f of t comma g of t, then the integral of r of t with respect to t would be the vector that has the integral of f of t comma integral of g of t. And that's true for indefinite integrals, and it's also true for definite integrals. So what I'm seeing here is that we're actually learning nothing new today. Okay, all you have to do is just calculate the same old derivatives, or sorry, the same old limits, same old derivatives, same old integrals that you learned in Calc 1. Okay? The same derivative rules apply. Let me show you that. Look at that box there. Okay? We have the same old sum and difference formula for derivatives. Same old chain rule. The quotient rule is the same. I don't know why they left it off here, but the quotient rule is the same. The constant multiple rule is the same. The only difference here is that the product rule is the same, but it's just that there's 3 of them, because when you have a vector valued function and you're going to multiply it times something, there's 3 different kinds. You can multiply times a real valued function, or you can multiply 2 vector valued functions using the dot product or using the cross product. But what's important though is look and see the product rules are the same in all of those. It's the derivative of the first times the second plus the first times the derivative of the second. Okay? What's the definition of continuity for a vector valued function? It's the same as it is for a real valued function. Okay, we say r of t is continuous at t equals c if the limit of r of t as t approaches c equals r of c. Same as the definition for continuity of real valued functions from Calc 1. Okay, so you see the point is that there's nothing new here, except just noticing that there's more than one kind of product, okay? But the product rule is the same for all the different kinds of products. And the only really the only new thing is just this idea of graphing. When you graph the derivative of a vector valued function at a point, you get a vector that is tangent to the curve at that point. And that's really the only thing that's new here. Whereas for a real valued function, the derivative is a number, right? And so it tells you the slope of the tangent line. But for a vector valued function, the derivative is actually a vector. It's a physical object. That's not just a number. It's actually a physical object. Okay, have a good afternoon.